All right, so far all that we've looked at are sort of qualitative views of how charges react to one another. We're going to do it more quantitatively now and use some of what we learned from the previous semester for charges. Now the qualitative stuff, you know, positive, plus and negative charges attract to one another, like charges repel. And that goes back to grade school. You should have seen that many years ago. But you may not have seen this before unless you had high school physics. Coulomb's law describes the force between two charges. It's given fairly simply. It looks like this. F between two charges. I'm going to call this the force between charge 1 and charge 2. So it's the force on charge 1 due to charge 2. You write that in words. This is, when I say F12, it's the force on Q1 due to Q2. Where Q1 and Q2 represents the charges here. And F12 is going to be equal to K, this is Coulomb's constant, Q1, Q2, divided by the distance between them squared. And we're going to do the absolute value of Q1 and Q2, so any signs that those have we won't include. All right, Coulomb's constant is K. Coulomb's constant has a value of 9 times 10 to the 9th. Let's see, that is in Newton meter squared per Coulomb squared. So you'll see that if I put in those units here, it leaves me, when I cancel out the Coulomb squared and the meter squared, it leaves me just with newtons, which is what I have here. Q is in units of coulombs, and R is in units of meters. So those are the SI units for both, for charge and distance. Remember, these charges are often very small, so I just want you to remember these metric prefixes especially. Now don't forget, you are responsible actually for all the metric prefixes that we had before, but we'll use these quite a bit, so I just want to remind you of these. Micro and nano. Micro is 10 to the minus 6, nano is 10 to the minus 9. I also want to remind you that you are also responsible for centi, milli, micro, nano, and we might see pico. You're not responsible for it, but pico, which is 10 to the minus 12. I'm going to put this in parentheses. All right, and then on the other side, you need to know, what is it, kilo for 1,000, mega, and giga. We'll see those more when we deal with light. Coulomb's law is similar in form and action to Newton's universal law of gravitation. So if you remember Newton's universal law of gravitation, it gave the force between two objects of mass. F was equal to big G, which is a gravitational constant, M1, M2 over R squared. So it's similar in form. It has this inverse squared relationship with distance, 1 over R squared. And the reason for that is that these force fields go out, we'll talk about fields in a bit, but they go out in a spherical pattern, and it gives this 1 over R squared dependence on the distance. So it's similar in form and action. That is how the forces act on one another. We'll deal with that in Newton's third law, to the law of gravitation. So as a result, some of the stuff that we'll talk about in dealing with electrical forces will be similar to what we dealt with when we discussed gravitational forces and vice versa. And in fact, we're going to get a lot into fields and what have you. And we didn't do that last semester, but you can extend a similar argument to gravitational forces, the use of fields to describe forces. Now, Newton's third law, if you remember, that applied to objects of mass. For example, the Earth is pulling down on me with 700 newtons, and likewise, I'm pulling back on the Earth with 700 newtons. So Newton's third law applies to all forces, but it particularly applies to field forces, that for every force, there's an equal and opposite force. And the same is true for charges. So the force on charge 1 due to charge 2 has to be equal and opposite the force on charge 2 due to charge 1. So if I have a force on this object, these are like charges, so they're going to repel. The force on charge 1 due to charge 2 And then I have a force on this object, the force on charge 2 due to charge 1. The magnitudes of these two forces are going to be equal. And in fact, they're going to be equal to the negative of the other because they're in opposite directions. So this is Newton's third law. For every force, F12 for example, there's another force that's equal but opposite that force. And so we see that exhibited very clearly here in Newton's third law for electric forces. Same can be true here for opposite charges. F12 will be in that direction. F21 will be there. So I have F12 is equal to the negative of F21. All right. So we dealt with the superposition principle, but just let me reiterate, and you will be seeing this quite a bit in this chapter especially, and in the next chapter. So a lot of vectors coming up. If you're having trouble with vectors, I recommend that you go back to last semester and review some of the stuff that we did on vectors. Or if you're still having trouble, let me know that there's some nice online resources, or of course you can come see me as well and I can help you with vectors. But you will be doing it a lot in these first couple chapters. So if you're having trouble with vectors, now's the time to get help. So when you have two or more charges, you can determine the force on one of the charges by doing the vector sum of the forces, adding the vector forces from the other two charges. So this is a pretty simple one. I have these three charges. I want to know what is the net force on Q3. So first I'm just going to draw the forces. I have two forces acting on Q3, the force due to Q2 and the force due to Q1. Now the force due to Q1 is going to be in this direction. So I'll label this as the force on particle 3 due to particle 1. So that's F31. The reason I drew it to the right is that both Q1 and Q3 are positive, so the force is going to be repulsive. All right. And then I have a force here, F, the force on particle 3 due to particle 2. All right. Those, since particle 2 is negative and particle 3 is positive, they're attracted to one another, and so the force will be towards particle 2. All right, so I know these. I want to find the net force. The sum of all the forces on particle 3 will be F31 minus F32. So now all we have to do is calculate the magnitude of F31 and F32, and we'll be able to find what is the net force. So let's see, I had, back here for just a second, just redraw some of this. F31 to the right, and F32 to the left. So I have F31 and F32. And now I want to find out what is F31. That's going to be K, Q3, Q1 over the distance between 3 and 1 squared. So I'm going to put in the numbers here. I'll do it in this case, but not thereafter. So that's 9 times 10 to the 9th. Q3 had a value of 4 coulombs. Q1 has a value of 2 coulombs. And then that's divided by the distance between them, which was 3 meters. And that's squared. So let's see, that's going to be 8 times 10 to the 9th. Newtons. All right, so that's going to be F31. Now let's also find F32. It's going to be 9 times 10 to the 9th. Q3, which was 4 coulombs. Q2 now, which is 2 coulombs, divided by the distance between particle 3 and particle 2, which is 2 meters squared. And that's going to be 18 times 10 to the 9th newtons. So now, if I want to find the net force, I just say F31 minus F32. That's going to be 8 times 10 to the 9th. minus 18 times 10 to the 9th, which is going to be, these are all in newtons. 10 times 10 to the 9th, or 1 times 10 to the 10th newtons. That's going to be negative. That means that my net force is going to be to the left, and it's going to have a magnitude of 1 times 10 to the 10th newtons. Right. That's a simple vector problem. You should know how to do that. You'll certainly see it on the test, and even some more complicated ones. We'll do a 2D problem next. Let me stop